To demonstrate Faraday's and Lenz's discoveries about electromagnetic induction, we designed an experiment to prove that a time-varying magnetic field produces an electromotive force, inducing current in a closed circuit. This was proven in two ways, one moving a magnet through a fixed circuit, and another by moving a wire with a fixed magnetic field.
The formula to obtain the electromotive force generated by a time-varying field is expressed as minus the partial derivative of the magnetic flux with respect to time. In other words, EMF is the change of magnetic flux with time. To prove this experimentally, we created the time-varying field by moving the magnet through the coil and by moving the wire inside the motor.
For the first demonstration, we used copper coils with 3 different diameters and 5 stacked neodymium magnets. We connected both ends of the coil to a multimeter in order to close the circuit and monitor the electromotive force generated.
We started off experimenting with the coil of the smallest diameter. By moving the magnet through this coil, we obtained voltages going from minus 2.5 to 2.5 millivolts. Next, repeating the same experiment with the coil of medium diameter, we got values of minus 2.7 to 2.7 millivolts. Finally, testing with the coil of the largest diameter, we got voltages ranging from minus 2.9 to 2.9 millivolts.
As a result, it was proven that the bigger the diameter, the greater the electromotive force generated in the closed circuit. Furthermore, we increased the number of turns in this last coil and measured a maximum voltage of plus minus 7 millivolts. Hence, the greater the number of turns, the greater the EMF.
We noticed that if the magnet was introduced into the coil in a way that the magnetic field was parallel to it, no voltage was generated. The electromotive force was only present when the magnetic field was perpendicular to the coil.
For the second experiment, we used an electric motor to produce an electromotive force. Bearing in mind that electric motors are built with a moving coil attached to a motor inside a cylindrical wall of magnets, we connected both ends of the motor to the terminals of the multimeter. Then, we manually rotated the motor's axis and observed that voltages of around 75 millivolts were generated. If the direction of the rotation was changed, the voltages generated were of the same magnitude with negative signs.